Hello friends, welcome to the online lecture series of Basics of Computer Networks. Myself, Assistant Professor Mr. V.R. Vadekar from Matoshi College of Engineering and Research Center. Students, today we are going to discuss multiplexing. But before that, let's have a quick revision that what we have studied in our last lecture. So guys, if you remember, we have studied types of signals. That is your analog signal, digital signal. In that also we have seen periodic, non-periodic signal. What is simple signal, composite signal. And then we have seen the time domain and the frequency domain plot of those signals. How to represent sine wave in mathematical form. Then we have seen the digital transmission of via using your low pass channel, band pass channel. So after this, today's topic that we are going to discuss is your multiplexing and analog transmission of our signals. So guys, there are two methods for the bandwidth utilization. How to utilize the bandwidth properly, that is by using multiplexing and spreading. Now, bandwidth utilization, it is a wise use of available bandwidth to achieve a specific goals. There are two categories, as I already told, that is multiplexing and spreading. So, if you want to achieve efficiency, then you can achieve it by using what? Multiplexing. But if you want a privacy and anti-jamming so that no intruder, it can jam your signal, hack your signal, then you can go for spreading. So guys, basically in your syllabus, we have multiplexing. So we are going to see multiplexing. So what is multiplexing? So it is a set of techniques that allows a simultaneous transmission of your multiple signals across a single data link. And whenever the bandwidth of a medium linking two devices it is greater than the bandwidth needs of the devices, the link it can be shared. So guys, if you have more than two sources and they want to transmit the information simultaneously, it is not possible to have a separate link, separate line between each transmitter and receiver. Because it is going to, practically it is impossible. It is going to cost a lot, as well as it is going to occupy the space a lot. So hence it is practically impossible. So that's why guys, we have to use a multiplexer. So you can see on this screen, there are n input lines are there. So it doesn't mean that we should have n channels. So we have only one link that is going to transmit these n input lines to the receiver. You can see it, observe it over here, it is called a multiplexer. Multiplexer, basically it performs operation of many is to one. How it is? Because n number of input lines are there and we are going to add this signal to make a composite signal. So as a one signal we are going to transmit it. So it is going to perform what? Many is to one at the transmitter side. This is a demultiplexer which does the exact reverse operation of your multiplexer. It performs the operation of what? 1 is to many. It means what the composite signal it is there, it is going to split into the n output lines, which is equal to the number of input lines. Now, categories of multiplexing. So guys, there are basically two types of multiplexing. Analog multiplexing and digital multiplexing. But in analog multiplexing, again there are two subparts, that is frequency division multiplexing and wavelength division multiplexing. And third, that is a time division multiplexing, which comes under what? Digital multiplexing. So basically, for analog signals, if you want to transmit the analog signal, we are going to prefer frequency division multiplexing. And for optical signal, for light signals, we are going to use wavelength division multiplexing. Whereas for digital signals in the form of 1 and 0, you require time division multiplexing. But guys, it doesn't mean that frequency division multiplexing, it could not transmit digital signals. It can. But before transmitting digital signal, we have to convert this digital signal into analog signal. And after converting into analog, we can use this frequency division multiplexing. So first category we are going to study, it is your FDM, that is your frequency division multiplexing. So FDM, it is an analog multiplexing technique that combines what? Analog signal. And these are going to modulate a different carrier frequencies. And then modulated signals are combined into a composite signal. And then it is going to transmit through that channel, whose bandwidth it is going to accommodate that modulated signal, that composite signal. And remember, the channels, it can be separated by strips of unused bandwidth, that is called a guard bandwidth, to prevent overlapping. Otherwise, two channels, two radio stations, if we are not going to separate it by a guard band, then the interference of these two channels, it is going to take place. So in order to avoid that interference, overlapping, we have to introduce guard band between two channels. Now, so the operation of this frequency division multiplexing is based on what? Sharing the available bandwidth of a communication channel among the signals that to be transmitted. Guys, what is the principle working? Principle working is that whatever the available bandwidth it has been given, we have to share that bandwidth. Although all the channels are going to be transmitted simultaneously, but they are going to modulate a different carrier frequency. See that many signals are transmitted simultaneously, with each signal occupying a different frequency slot within a common bandwidth. And each signal that is to be transmitted, it can modulate a different carrier, and the modulation, it could be your amplitude modulation, it could be your FM modulation, phase modulation, or single sideband modulation it could be. Then these modulated signals are then added together to form a what? Composite signal, which is transmitted over the single channel. Now you can see the spectrum. See, this is the bandwidth of your overall communication channel. This is the bandwidth of overall communication channel. And this is the bandwidth of individual channel, which has a center frequency FC1. This channel, it has a carrier frequency FC2, FC3, FC4, like this one. So this is the bandwidth of single channel, and this is the bandwidth of what? Overall communication channel. So you can see from this figure, see how the spacing it has been introduced. This is called a guard band. We are not going to overlap your channel 1 and channel 2 because information might get lost. So it is better to introduce some gap between these two channels. Now you can see by means of this figure, you can understand the FDM process. So basically, suppose these are the signals, different signals which has a common bandwidth. This is signal 1, 2 and 3. So at your multiplexer, at your transmitter side, there is a modulator. See, there are 3 signals, so we have required 3 modulators. And each modulator, it is going to tune to a different carrier frequency. Modulator 1, it is assigned tuned to a carrier frequency F1. This is F2 and this is F3. You can observe the frequency. See, the frequency of F3 is greater than F2 and the frequency of F2 is greater than your F1. And over here, the output of modulator, it is nothing but your modulated signal. Over here, we are going to do the modulation. So here, modulation you can do, it could be your amplitude modulation, it could be your phase modulation or frequency modulation. So can you tell guys which modulation technique we have used here? Which one? So if you observe it carefully, the frequency it is not going to change. What is going to change? The amplitude of this carrier frequency, it is going to change. It means this modulating signal, it is going to modulate the amplitude of this carrier F1. So it is what? Amplitude modulation. This is the first output of your modulation. This is the second output. See, the amplitude of this modulator F2, it is going to change the instantaneous value of this modulating signal. But frequency, phase, it remain constant. Only amplitude is going to change. And this is the third one. That is, see the amplitude again, it is going to change according to the instantaneous value of your modulating signals. So these are the three modulated signals. And then these modulated signals are added to form what? Composite signal. And this composite signal, it is transmitted through a shared bandwidth or shared link. So it all happens at your transmitter side. That is a FDM, multiplexing. Now we will see the demultiplexing, that how it is going to occur at your receiver side. Now guys, at the receiver side, this is the composite signal that we received, which consists of three different modulated waves. So we have three different bandpass filters are there. Filter 1, filter 2 and filter 3. So what is going to be happen? This filter 1, it is going to pass the frequency of F1 and its sidebands, whereas it is going to block F2 and F3. Similarly, second filter, it is going to pass only the carrier frequency F2 and its sidebands, and it is going to reject F1 and F3. And this is your bandpass filter third, which is going to pass only the frequency related to your F3 and rejecting your F1 and F2. So this is the demodulator. So demodulator, what is it is going to do it? See, these modulated waves are applied to demodulator. Demodulator, it is going to tune to a carrier frequency F1. Second demodulator, it is tuned to carrier frequency F2, and this is to F3. And the output of this demodulator, what it is going to do it is going to remove this carrier, and what remained? Your original signal that you transmitted. Similarly, it is going to remove this, and this is your received signal. That is your baseband analog signal. So hope so with the help of this waveform you understood this FDM. Now guys, again, if you didn't understand from this wave example, you can understood it. See, these are the three voice channels are there. Suppose it has a range bandwidth, it is of 0 to 4 kilohertz, 0 to 4 kilohertz or 0 to 4 hertz, you can say in example. At the transmitter side, multiplexing side, there is a modulator. Modulator, see what it is going to do it. It has a carrier frequency. It is going to do the modulation, and it has a range of frequency for 20 to 24 hertz or kilohertz, you can say. Since these signals have a common bandwidth, that is a 4 kilohertz, but we couldn't allocate the second voice channel into the same range, that is 20 to 24 kilohertz. Why? Because overlapping, interference, distortion would occur. So that's why what we are going to do it, we are going to assign the second channel to a frequency from 24 to 28 kilohertz, because bandwidth is a 4 kilohertz. And similarly, the third voice channel, we are going to assign a bandwidth from 28 to 32 kilohertz, that is 28 plus 4. Then these three modulated signals are added to form a composite signal, which ranges from 20 to 32 kilohertz. This is your composite signal. And it is going to sent via this higher bandwidth link, received at the receiver. And over this is your demultiplexer, where the composite signal, see, it is splitted into a three different modulated wave. For that, what we have used? Bandpass filter, three bandpass filter. This bandpass filter, it is going to pass 20 to 24 kilohertz band, whereas it is blocking 24 to 32 kilohertz. Similarly, band pass filter 2, it is going to pass only this range, that is 24 to 28 kilohertz, and rejecting this and this one, that is in blue and green color it has been shown. Similarly for third band pass filter. Then after this we are going to apply to the demodulator. Then demodulator, it is going to remove this carrier frequency. And what is remain, what we get, it is a 0 to 4 kilohertz original signal that is being transmitted. Similarly, this is your second baseband analog signal and this is your third analog signal. So hope so guys you understood this. Now, wavelength division multiplexing. So analog, it is also a type of analog multiplexing technique which is used to combine what? Optical signal. And conceptually guys, same working principle as it of your FDM. So basically light signals are transmitted through this fiber optic channels, which is denoted by C, lambda 1, lambda 2 and lambda 3. And this is a symbol of your optical pulse. And over here, this is your multiplexer, this is your demultiplexer, that is many is to 1 and 1 is to many operation. Principle is same. See the wavelength 1, 2, 3, we are going to combine it to form a composite signal. That is combining different signals of different frequencies or wavelength we can say. Lambda is your wavelength. And again at the receiver side, at the demultiplexer side, it is going to split into a 3 its original signals, that is lambda 1, lambda 2 and lambda 3. Now combining and splitting of this light source are easily handled by a prism. This is your prism which could be act as your multiplexer as well as demultiplexer. Because prism, it can bend a light beam based on the incident angle and the frequency. So over here guys, lambda 1, that is at the transmitter, this is your source 1. It can only transmit this wave to the receiver, that is lambda 1 only. It could not transmit information to lambda 2 and lambda 3. And similarly, lambda 2, that is a source 2, it can transmit its information to only the source 2 at the receiver. It could not transmit it to your source 1, this receiver 1 and receiver 3. And similarly, lambda 3, it is going to pass this information to only this receiver number 3 only, not to receiver 1 and 2. So it is called a fixed WDM. It means what? The 3 fibers come together at a prism, each having energy in a different band. After passing through the prism, beams are combined into a single shared fiber for transmission to a distant destination where they are split again. But since the bandwidth of a single fiber, it is about 25,000 gigahertz, that is a much greater potential for multiplexing many signals, that can transmit over a long routes. And what I explained, that we have a fixed WDM system, that the bits from fiber 1 at a source, it can be given to the fiber 1 at a destination only. So it could not go to fiber 2 and fiber 3. Similarly for fiber 2 and fiber 3, what I explained. So that is called what? Fixed WDM system. So guys, you can use a switch WDM system also. How? By assigning a tunable filters at the receiver. See, it means switch WDM system in the sense what? The fiber optic source 1, it could transmit information to the receiver 1, 2, 3, anyone. It is not a fixed, it is a switch WDM system. So for that what we required a filter which is a tunable, which can be tuned to any frequency, any wavelength. Similarly, lambda 2, that is a fiber optic, the source 2, it can send its information to any receiver. So either you could have a tunable filter at the receiver, or second option is that you could have a tunable filters at the source, at the transmitter side. Or you can have a tunable filters at both the side, both the premises. but it is a wastage of money. If I am going to achieve my desired aim objective by using just a tunable filter either at the transmitter or receiver side, then why to install at both the sides? So hope so you understood your fixed WDM system and switch WDM system. Now, next it is your time division multiplexing. So, time division multiplexing, that is a digital multiplexing technique for combining several low rate channels into a one high rate one. See, these are the number of sources 1, 2, 3, 4. Over here, guys, all the bits are not going to be transmitted simultaneously. They are going to be transmitted serially, one by one. Each, you can see from the figure that what we are going to do it. This is a frame 1, this is frame 2 and frame 3, and in each frame we are going to take a bits, we are going to take the data from each source serially. First we have taken the data from source 1, then source 2, 3 and 4. So this complete cycle it has been over. So it is your frame 1. Next, after sending this to the demultiplexer, again it is going to be this 1:many operation, it has happened over there, and after transmitting this, the second frame it comes. So second frame again it is going to take the data from either from source 1, then source 2, 3 and 4 serially, and it is going to send it serially. So for a very short duration they are going to take the bits from each source, and this process it goes on. So in synchronous TDM, it could be synchronous and it could be asynchronous. So the data rate of the link is n times faster and the unit duration is n times shorter. You can understand it from this example. That see, there are three sources are there, A, B and C. And we are going to split the information from the source to A1, A2 and A3. Information by source B, it is split into B1, B2, B3. So as like this one. So we are going to take the data from each line. See, this is a frame 1. So we are going to take the data first from A1, source A, then B1 and C1. So one frame it is completed. And so each frame it is a 3 time slot because 3 sources are there. So if the duration of each frame, suppose it is a T second, capital T second, then what would be the duration of each slot? It could be definitely T by 3 or T by N. What is N? N, it is a number of sources. Or how many number of slots are there in that frame? So similarly, you have made frame 2 and frame 3. So frame wise, these data are to be transmitted. So what I explained that in TDM, all the signals that to be transmitted are not transmitted simultaneously. Instead, they are transmitted one by one. So each signal will be transmitted for a very short time, and the one cycle or a frame is said to be completed when all the signals are transmitted once on this transmission channel. And as shown in the previous figure, what I explained, there are 3 sources ABC, which is divided into units A1, A2, A3, B1, B2, B3 and C1, C2, C3, etc. Like that. Then one unit from each source is taken, combined to form a one frame, and the size of each unit, it could be what? 1 bit or it could be several bits also. Okay guys, so our multiplexing it is over. Now, the next topic that we are going to start, it is your analog transmission. Now, analog transmission, guys, it means we have a 2 types, that is analog to analog conversion and digital to analog conversion. Now, analog to analog modulation, first we would see this one, that analog to analog conversion, it is a representation of analog information by an analog signal. And modulation is needed, guys, if the medium it is what? Band pass in nature, or only if only a band pass channel is available to us. Because For band pass channel, it has a range from low frequency to high frequency range. So for that purpose, you require a modulation, guys. Because without modulation, the signal, it could not travel a longer distance due to its limited energy or power content of that signal. So you can see this is amplitude modulation, frequency modulation and phase modulation. There are three types of modulations are there. So in amplitude modulation, you can see it from the figure. This is your modulating signal. This is your carrier signal. And since it is an amplitude modulation, in the sense what? This modulating signal, it is going to modulate the amplitude of this carrier signal. So you can see this is the output modulated signal whose amplitude it is going to change with respect to the instantaneous value of your input signal. And this is a block diagram for it. In order to generate your carrier wave, we require oscillator. This is your modulating signal, multiplier, and the output is nothing but your modulated output. But remember guys, the total bandwidth required for AM, it can be determined from the bandwidth of audio signal. If the bandwidth of audio signal, it is a B, then the bandwidth of amplitude modulation, it would be what? Twice of B. So remember this one. So this is your total bandwidth of your system. See over here, that is an AM band allocation. If bandwidth of audio signal, that is your speech and music signal, it is usually 5 kilohertz and it's ranging from 530 kilohertz to 1700 kilohertz. And you can see it over here that we have allocated each separate band, it has a bandwidth of 10 kilohertz. Bandwidth of this channel is 10 kilohertz, 10 kilohertz, 10 kilohertz, like that one. Right? Now, frequency modulation. Now in frequency modulation, modulating signal, it is going to modulate the frequency of the carrier wave, keeping its amplitude and phase constant. In previous example, only amplitude it is going to change, whereas frequency and phase remain constant for amplitude modulation. So similarly, for frequency modulation, the frequency it is going to vary. So see, if the modulating signal it is going to increase towards its peak, then frequency it is going to increase. And when it is going to go into the negative cycle, the frequency it is going to decrease. And for that purpose, guys, we required a voltage control oscillator. Why? Because the frequency of this oscillator, it is going to change according to the voltage of your or amplitude of your modulating signal. And bandwidth of that FM system is equal to twice of 1 plus beta into your B. Whereas beta, it is nothing but your modulation index, right? So in that, as you understood, frequency is going to change, whereas phase and amplitude it remain constant. Now, you can see the FM band allocation. So bandwidth of audio signal, that is your speech or your music signal, you know, it is broadcast in stereo, it is almost 15 kilohertz. And FCC, it is going to allow a 200 kilohertz for each station, beta equal to 4, modulation index equal to 4, which is going to be separated at least by 200 kilohertz. As it is going to, the bandwidth of the system, it is going to ranges from 88 megahertz to 108 megahertz. This is the FM band allocation. This is the bandwidth of that FM system. So if you have many FM stations are there, suppose it has a FM station, say it is a Radio Mirchi, right? So whose frequency it is going to start from 88 megahertz, but it is going to allow for what? 200 kilohertz for each station. So since it's starting, that is FL, it is 88 megahertz, then what is the FH for this station? It would be what? 88.2 megahertz. And they are going to tell that the separation guard band between these two stations, it could be what? 200 kilohertz. So suppose it is a Radio Mirchi whose frequency ranging from 88 to 88.2 megahertz, and this is a second FM station whose frequency then it should be start from what? 88.4 megahertz up to 88.6 megahertz. See guys, because these two stations, that is Radio Mirchi and this is Red FM, they are going to be separated by what? 200 kilohertz. It is just example guys. And the bandwidth of this each station, it is also 200 kilohertz. So 88.2, 88.2 megahertz, it is the bandwidth of this channel 1, station 1. And its station 2, it is going to start from 88.4 to 88.6. And so on. Then 88.6 to 88.8 megahertz, it is a separation between these two channels. Now, next it is your phase modulation. Phase modulation, the bandwidth, it is same as twice of 1 plus beta upon bandwidth of your modulating signal. So you can see it over here. This is your modulating signal. This is your carrier signal. See how the modulated wave it is going to occur. See the phase it is going to change at this instant, phase, whereas its frequency and amplitude remain constant. Understood? In phase modulation, what is going to be changed? Phase of the carrier signal it is going to change, keeping its amplitude and frequency constant. So hope so you understood this analog modulations. Now, next it is your what? Digital to analog conversion guys. So it is the process of changing one of the characteristic of analog signal based on the information in your digital signal. This is your digital data. So we are going to do the modulation. We are going to change the characteristic of that analog signal. Now, the types of digital to analog modulation, it is your ASK, that is amplitude shift keying, frequency shift keying, PSK, that is a phase shift keying. So basically guys, ASK, it is analogous to your amplitude modulation that we have studied. FSK, it is analogous to FM modulation, and PSK, it is analogous to PM, phase modulation. So in it, amplitude it is going to change, keeping frequency and phase constant. In FSK, amplitude and phase is going to be constant, frequency is going to change. And for PSK, phase is going to change, keeping frequency and amplitude constant. And there is a hybrid modulation that is called a CAM, that is quadrature amplitude modulation. In this, amplitude and the phase is going to change, frequency remain constant. So two characteristics are going to change of the carrier, that is amplitude and phase. That is nothing but your quadrature amplitude modulation, but it is not in your syllabus. So we are going to discuss only these three parts. Now, before studying this, we should have a clear about the signal element and data elements. Data elements are what we need to send, that is the bits, and signal elements are what we can send. So you observe this figure. This is called a signal element guys, one signal element. This one signal element, it is going to be represented by logic 0, or only one bit it is there. So one data element per one signal element, therefore R is equal to what? 1. That for one signal element, how many bits are there? Only one bit it is there. So R equal to 1. Now, if you can observe this one, there is one data element, but per two signal elements are there. Two changes are there. See, these are called as signal elements. It means logic 0, it is represented by half bit duration by this negative voltage, and then it makes a transition to the positive voltage, that is a half of the bit duration, it is represented by this positive voltage. So it means logic 0, that is 1 bit, it is represented by 2 signal elements. So what would be R? R equal to 1 by 2. Why 1 by 2? 1 stand for 1 data element and 2 stand for 2 signal elements. Similarly, over here, one signal element it is there. But this one signal element, it is going to carry how many bits, how many data? 0 and 1. So 2 data elements per one single element. So R is equal to what? 2 by 1. 2 is what? 2 data elements and 1 it is your signal element. And last, you can see it over here. This is your signal element. That is 3 signal element. 1, 2 and 3. But these 3 signal elements, how many data it is going to carry? How many bits it is going to carry? 4. So R is equal to what? 4 by 3. That is 4 means 4 data elements and 3 means 3 signal elements. It is, guys, same as like that signal element. Suppose you are traveling by a car. So car, it is nothing but your signal element. And in that car, how many passengers are there? It is going to tell you the data element. Simple. For your, you can easily remember that. Understood, guys? So data rate, it is going to define the number of data elements, that is the number of bits sent in 1 second. It is measured in BPS, that is bits per second. And what is signaling rate? It is a number of signal elements sent in 1 second, which is also called as what? Baud rate. So data rate, it is nothing but your bit rate, whereas signal rate, it is also called as pulse rate, modulation rate and baud rate. So we can write it as S is equal to C into N into 1 upon R. What is this? N, it is the data rate. That is the number of bits transmitted per second. C, it is your case factor. S, it is the number of signal elements. And R, it is what? It is a number of data elements carried by each signal element that we have seen in the figure. And remember, guys, bandwidth is proportional to the signal rate, not data rate or bit rate. The bandwidth is proportional to baud rate. Because, guys, baud rate or signal element, in the sense, you can assume a car. So how many cars are going to pass on the road, through a road on any national highway? That is going to decide its lane. If more traffic it is there, then we have a 4 lane, 6 lane, right? It is not going to be depend on the how many passengers are traveling in that car. Getting, guys? So how many lanes are there? It is not depend on the number of passengers traveling through that bus or through that car. It is the number of vehicles, number of cars, number of bus that is going to decide the bandwidth. So over here, baud rate, that is a signal element, it is going to determine the bandwidth. And the minimum bandwidth, it is given by C into N into 1 upon R. And the maximum data rate, N max, it is given by 1 upon C into B into R. And for the numerical point of view, you can write this one. That is a data rate versus your signal rate, that is a bit rate versus your baud rate. So signal rate S is equal to N into 1 upon R baud. Because unit of signal rate, it is a baud. N, it is nothing but your data rate, and what is R, small r? It is a number of data elements in one signal element. And always remember, guys, bit rate is always greater than or equal to baud rate. Now, so we can start with your binary ASK. That is, or simple ASK, which is also called as on-off keying. So you can see if you have a digital data 1 0 1 1 0. So we have amplitude. So peak to peak amplitude, it remains same. See, one signal element. Amplitude, it is going to change. For logic 1, the peak to peak amplitude is constant. But for logic 0, amplitude is 0. For logic 1, amplitude, peak to peak amplitude is constant. But for logic 0, it is a 0. So you can see that in 1 second, this is going to represent 1 second. So in 1 second, how many bits are going to be transmitted? 1, 2, 3, 4, 5. 5 bits are going to be transmitted, guys. So what is the bit rate? 5. But since each signal element, it is going to contain only 1 bit. So how many signal element it is going to travel? 5 signal element it is going to travel. So baud rate it is also equal to 5. Understood, guys? ASK, and understood about the bit rate and baud rate. Simple, consider, guys, baud rate it is nothing but your car. So you can represent each car. There are 5 cars are there, and each car it is going to carry only 1 passenger. So they are going to be travel in 1 second. So how many passengers are there? 5 passengers are there. And since each passenger, it has a different each car. So how many cars are there? 5 cars are there. So bit rate and baud rate equal to 5. This is the implementation of your binary ASK. This is your oscillator which is generates your carrier wave, and this is your digital signal in the form of your 1 and 0. We call it as binary because it has only 2 possibilities, either 1 or 0. So when we are going to apply to multiplier, the output of multiplier it is nothing but your binary ASK. Next it is your FSK. So see over here, FSK, frequency of carrier wave it is going to change. See, it has a different frequency. Amplitude, peak to peak amplitude, it remains constant for each logic. But for logic 1, high frequency it is transmitted. For logic 0, it is low frequency it is transmitted. And it goes on. So over here also bit rate 5 and baud rate it is also equal to 5. And this is your implementation of your binary FSK, that is a voltage controlled oscillator. That is, depending on the voltage of this input signal, modulating signal, the frequency of this carrier wave it is going to change. See how fast it is going to change. That is, the frequency is high, but time period it is less. Over here time period it is more, and hence frequency is less, because frequency and time period both are inverse in nature. Next it is your PSK. See, you can see from the figure that phase it is going to change. Whenever there is a transition from 1 to 0 or 0 to 1, there is change at the phase, keeping its frequency and amplitude constant. But whenever there is a no transition, see 1 to 1 no transition, 0 to 0 no transition, there is a no phase change. But when there is a change from transition from 0 to 1 or 1 to 0, then there is a change at its phase. And this is the implementation of your binary PSK. So hope so guys you understood today's lecture. So in today's lecture we have studied what we have studied, guys. We have studied about a multiplexing, different types of multiplexing. That is your FDM, WDM, TDM. TDM it is a digital multiplexing, and both that are analog multiplexing. After that we have studied the analog transmission. That is analog to analog and digital to analog. Then we understood about what is bit rate, what is baud rate. So hope so you understood today's lecture, guys. This is the assignment. So you have to please note down this assignment. In next module, we are going to study about the digital transmission of signals. That is analog to digital and digital to digital. So here it is my email address. For your assignment or any feedback, you can post it to on my this email address. Thank you very much guys for today's lecture. Thank you and have a nice day.